Okay, today we are going to talk about the double angle formulas. The section in your book is technically called the multiple angle properties, but this section gives us formulas for sine 2a, cosine 2a, and tangent of 2a. And you'll be using those to work on identities, proving that one thing equals another thing. But there's this one style of problem I want to show you. And here's the example. If I give you the tangent of an angle is 4/3, and I tell you that this angle A terminates in quadrant 3, then I'm just giving you some info about the angle. Here's the angle A, and whatever that angle is, its tangent is 4/3. And this is the type of problem where we're not really going to have to find the angle. We're just going to set up a little triangle. And if the tangent is 4/3, remember that's opposite over adjacent. Technically, that's -4 over -3 to make 4/3. Since we're over in quadrant 3, we're going left and down, which makes our hypotenuse 5 because it's a 3, 4, 5 right triangle. The question is, if this is where A exists, and by the way, I have to tell you it's in quadrant 3, so you know it's not up here, which would have different sines, cosines, and tangents. So let me get rid of that. If this is the case, then I'm going to use the formulas given in this section along with this triangle setup to solve for sine 2a, cosine 2a, and tan 2a. So let's start with sine 2a. Sine 2a's formula, let's call this part A, finding sine. Sine of 2a's formula is sine 2a equals 2 sine A cosine A. Now, this is going to be given. You're going to have this big list of trig identities, so it's not something you have to memorize. It's just something you have to use. So sine 2a is going to be based on this angle setup, the sine 2 times the sine of 2a times the cosine of 2a. The sine of A, I mean A, not 2a in that last statement. Sine of A is the opposite over the hypotenuse of this triangle. So the opposite over the hypotenuse is -4/5. All right, and because I'm going downward, I know it's got to be negative. That's why that -4 is important to have on your triangle. The cosine of A is adjacent over hypotenuse, or -3/5. Okay, so finding the sine of 2A is as easy as multiplying that together. And it looks like we're going to get 25 on the bottom and 24 on the top. 24/25. Okay, so notice, I never had to figure out what the angle was. I just needed to set it up and then use this formula to solve. Okay? Cosine of 2a. What you'll notice is when you look at the cosine double angle formula, there are actually 3 options. And the book goes through starting with one and, deriving and getting to the other 2. It doesn't really matter which one you use. You should end up with the same thing either way. So I'm just going to choose one. I'm going to choose 2 cosine squared A minus 1. You could choose one of the other 2 off of your formula sheet and do just as well. Okay, so 2 cosine squared A. I've already determined that the cosine is -3/5. I'm going to square that. Remember that squared after cosine before A means to take the cosine of A and then square it. -1. So this is 2 times the quantity -3/5 squared is 9/25 -1. So that's 18/25. And I'm going to go ahead and subtract 1 in the form of 25/25. And 18 minus 25 is -7/25. Okay, so remember, this is the cosine of doubling my angle. Just so you can keep in mind what we're dealing with here. A is over here. If 2A is doubling A, this angle is somewhere in the 3rd quadrant where it's somewhere between 180 and 270. So 2A is going to be somewhere between, let's see, 360 and doubling 270 is going to be 540. So 2a is going to be, somewhere up here on the top. So I just wanted to bring that up because the values that you're getting aren't the sines and cosines of this triangle that we drew. They're the sines and cosines of doubling that angle, wherever that angle happens to be. It's just you skip the step of actually finding what that angle is. Because we're working by hand, we're not working with a calculator. Okay, so anyway, back to this. What is the tangent of 2a? Well, the tangent formula is 2 tan a over 1 minus tan squared a. Okay, so using my triangle, 2 times the tangent of a is going to be 2 times the tan was 4/3, which was given at the beginning, over 1 minus tan squared, and tan squared is going to be 4/3 squared. So on the top I have 8/3, and on the bottom I have 1 minus 16/9. Okay, so that is 8/3 over 1 minus 16/9, or 9/9 minus 16/9 would be 9 minus 16, negative 7/9. Okay, so this is 8/3 dividing by negative 7/9 is multiplying by negative 9/7. Do a little canceling, and I get negative 24/7. So to review this example, our goal was to find, given some info about A, we didn't get the angle A, but we got where its tangent is, which let us set up this triangle system. We found the sine, cosine, and tangent of 2A using our new formulas. I'll give you one more quick example of a proven identity type of question with that involves our new formulas. So I'm going to prove that tangent y is equal to sine of 2y over 1 plus cosine 2y. Okay, so one of our important strategies for proving identities is usually we're going to start with the more complicated side, which for us is the side on the right. Given that this is in the double angle section, I'm most likely going to use my double angle formulas. So let me just start with sine of 2y. The formula for sine is sine of 2y is 2 sine y cosine y. And on the bottom, I've got 1 plus cosine 2y. I'm going to take out that cosine 2y, and I'm going to choose one of the three. Now, one thing that makes this tricky is you don't know which one of the three is going to work out nicely, so you might have to try one and then try another. I'm going to go with 2 cosine squared y minus 1. All right, one thing you have to be patient with these because you might try something and get a dead end and realize you aren't going anywhere, or you're working in circles. But just be patient with them and keep plugging stuff in, and you'll eventually make it work. Remember, I'm trying to make the right look like the left. And because I had these double angles, it made sense to me to try those. Okay, so let's keep moving. What happens here on the bottom is that the two ones cancel, 1 minus 1, and then you can start to see it take shape. I've got a 2 and a 2 that can go away. I've got a cosine and an extra cosine there, so I'm left with just sine y over cosine y, which equals tan y. And we have set out to prove that those two things were the same, and we've done it. Okay, so let me just encourage you again. You might see it within, one step or two. I see where this is going, but with these, you have to show how you get from, point A to point B to point C. You can't be right here and think, yeah, okay, I see the ones are going to go away, then I see the cosines are going to cancel, and I see the twos are going to cancel, and I'm going to be left with sine over cosine, which is tangent, and say, oh yeah, here we go, tan. You know, I appreciate that you can think those steps out in your mind, but you cannot just go straight to tan, because that's the whole question. Show that it's equal to tan. All right, you might be able to do all 1, 2, 3, 4 steps in your head, but if that were the case, then everybody could just write the answer and be done, because the answer is a part of the question. So anyway, that is your double angle section, section 14.4 in the book, and that's that. Young out.